Now we'll be taking the another one unit, that is semiconductor. Semiconductor are the different class of the substance. We are familiar with the metal, which are conductor, very good conductor. Their conductivity lie between 10 power 8 to 10 power 2 Simon per meter. Simon is a unit for the reciprocal of the ohm, we call Simon per meter. There's another one class of the material which don't allow electricity to flow at all, we call insulator. Insulator has got the conductivity 10 power minus 7 to 10 power minus 9 Simon per meter. They are the insulator. Perfect insulator for the current, electric current. Then in between the two, there lies a group of the substance we call semiconductor. Their conductivity is lesser than that of the same metals, but greater than that of the insulator. It lies between 10 power 5 to 10 power minus 6 Simon per meter. They are the element from the 14th group of the periodic table. Why we are interested in semiconductor? Why they are so important for us? The semiconductor are important for us because their property, their conductivity can be changed, can be moderated, can be modified according to our requirement. So this is a great advantage for us, right? Before we discuss about the semiconductor, let's first talk about the energy band. When there is a single electron orbiting the nucleus in an atom, the energy of the single electron we represent, or energy of the orbital in which one electron is moving, we represent by a single line. Graphically we represent by the single line. Now if a number of the atoms are closely packed, like 3 atoms are closely packed, so their outer orbital, whose energy we are representing by the single line, they overlap. Then overlap orbital, the energy of the overlap orbital, we represent a 3 closely packed line here, as the 3 atoms are closely packed, their 3 outer orbit overlap. So overlapped orbital, the energy we are representing by 3 line. All the 3 have got the same energy, but still we are not representing by the single line, because by the Pauli exclusion principle they cannot have. They are not permitted to have the same value of the energy, same value of the quantum state, right? Now, but when the atom are tightly packed, when the substance form solid, crystal, in the crystal the atoms are large number of the atoms are very closely packed. In that case, when large number of the atoms are closely packed, their number of the outer orbital overlap, and these energy of the overlapped orbital, which almost have got the same energy, is represented by a group of the closely packed energy level, and this group of the closely packed energy level we call energy band. So energy band is what? Energy band is group of closely packed energy level. When it form when large number of the atoms are tightly packed in a crystal. They are close so that their orbital overlap. Energy band are of the 2 types. First is valency band, and the second is conduction band. Valency band is the energy band which include the energy level of the valency electron. These are the electron, these are the energy level which is outermost and filled. So in an atom, the energy band formed due to overlapping of the outermost completely filled energy level is called the valency band. It consists of the valency electron, right? So the energy level, for example, if we have got the 1s2, 2s2, 2p6, 3s2 and 3p, 3p2 is a structure of the distribution of the electron in, say, silicon, then the energy band formed due to the overlapping of the outermost, which is completely filled energy level, we call valency band. All levels all quantum state are occupied, all energy level are occupied. The second, above this, the unfilled energy level. After the filled electron energy level, the next higher energy level, which is empty. Energy band formed because of the empty energy levels higher next to the filled one. or we'll say the lowest of the unfilled one energy level we call conduction band. We call it conduction band because electron once reach in the conduction band, it can move. Have you understood? The conduction band energy level is the one which is unoccupied. It consists of those energy level which are unoccupied. This is the lowest energy level of the conduction band. Valency band is the energy group of those energy level which are already occupied. Is occupied. No energy level is free. No seat is vacant for the electron to move around. This is the valency band. So it is valency band is the highermost energy occupied, completely filled energy levels. And conduction band consists of lowermost unoccupied energy levels. Right? Now this is the energy level of the valence band, highermost. In between the conduction band and the valence band, there is a gap. There is a difference of the energy. This difference of the energy we call band gap. The third thing come over here, the band gap. The band gap is the difference of the energy between conduction band and the valence band. In the different metals, different substance, different element, the value of the band gap keep on varying. And this can also be modified by adding some, making the alloy, making the semiconductor, in the process of the semiconductor, we can change the band gap, right? It can be changed. But this is the difference. This is also called the forbidden gap. Its another name is forbidden gap. Why we call it forbidden gap? Because electron cannot exist in this gap. It will be either in the valence band or it got the conduction band. They have no permission to stay in this difference, in this gap between the conduction band and valency band. Now on the basis of this energy, let us see that how the energy levels are arranged in the conductor, insulator and semiconductor. In the conductor, in the metals, which are very good conductor of the electricity, there are the two cases may be possible. The one, the conduction band is partially filled like this, or valency band is partially empty. In both of the cases, even at the normal temperature, its electron can move because there is a loss of the free energy level are there and there are the electron. They can move in this. So even at the room temperature or even at the low temperature, electron gets sufficient energy to move. So in either of the case, the metal will behave like a conductor because it don't require much energy for the electrons to move in the conductor and make it conducting. Other one case may be, which is most common case, atoms are so tightly packed in the crystal structure of the atom, of the metal, that conduction band and valence band overlap. When conduction band overlap the valence band because of the tight packing, then loss of the electron of the conduction band of the valence band become part of the conduction band. For them, there is a loss of the free energy level are available. So with a little bit amount of the energy, these electron from the valence band, they can go to the conduction. Here, only one type of the charge carrier will be there. What one type of the charge carrier? Charge carrier will be only electron. They will be moving all around. Now let's talk about the insulator. What happened in the insulator? In the insulator, conduction band is empty, so no free electron is there to conduct. Valence band as usual fully occupied, so its electron has no freedom to move around. And the forbidden gap, the band gap, is very large, is of the 3 electron volt. So it is difficult for the electron to go from valence band to the conduction band even on gaining the energy. It is very difficult for them. They cannot easily go to the conduction band. So the metal behave, the substance behave like an insulator. Substance behave like an insulator in this case because electrons are not present. So in a normal condition, there is no free electrons to move around in the conduction band. And even when you change the condition, when you supply the energy, not possible for the electron to go from valence band to conduction band. So this substance will behave like an insulator. Now we come to the semiconductor. In the semiconductor, what happened? In the semiconductor, as you observe, the conduction band is empty. In a normal condition, there is no free electron available. Valency band is completely occupied. All the energy level are occupied. Electrons are there. And the forbidden gap is small. It is less than 3 electron volt. It is almost of the order of the 1 electron volt. So what? If it is a 1 electron volt, so what's the benefit? The benefit is that if you supply the energy, if you rise the temperature, or if you supply the energy by applying the potential or some other way, if you supply the energy to these electrons, they can easily jump from valence band to the conduction band. It will be easier for them to jump from valence band to the conduction band. So result is that electron now will be reaching to the conduction band, and they find the loss of the free energy level, and they can move in these energy level. They can move in the energy level, and this way the conductivity will increase. So here, one important thing, with the increase of temperature, with the more supply of the energy, more and more electron from valence band will reach to the conduction band. The result is that with the rise of temperature, the conductivity will increase in case of the semiconductor. One more interesting thing which differentiate between the conductor, metal and semiconductor. In the semiconductor, when electron jump to the conduction band, it leave behind a positively charged vacancy in the valence band. And this positively charged vacancy we call hole. Is a vacancy which leave behind. For example, if the student go from filled class to the vacant class, they leave behind a vacant chair. These vacant chairs is like an hole here in the valence band. These holes have got the permission to move in the valence band. Now how these holes can move? The electron from the lower energy level may come over here, and they occupy the hole, and the hole may shift down deep in the valence band. So simultaneously in the semiconductor, two type of the charge carrier. Two type of charge carrier. One is electron in conduction band, and second is hole in valence band. While in the metal, it was only one type of the charge carrier, electron. In the semiconductor, two type of the charge carrier are there. Semiconductor, as we have discussed, are again of the two type. One is intrinsic semiconductor, other is extrinsic semiconductor. Intrinsic semiconductors are the pure crystal of the semiconductor. In the intrinsic semiconductor, conduction band is empty, valence band is completely occupied. Forbidden gap is of the energy of about 1 electron volt. In case of the intrinsic semiconductor, whenever you supply energy, electron and hole pair is created. As the electron jump from valence band to conduction band, the one electron is there, then one hole is left behind. So electron density in conduction band will be equal to the hole density in the valence band, right? And that we call intrinsic charge density, Ni. Ne is equal to Nh is equal to Ni. Ni is intrinsic charge density. These pure semiconductor are of little value for us. Their conductivity can be modified by adding some other one atoms, the atom from the other group into the crystal. So we got a modified semiconductor that we call extrinsic semiconductor. Extrinsic semiconductor are the crystal in which the conductivity is modified by adding some impurity from the other element, from the other group into the pure crystal of the semiconductor. The process of adding the impurity we call doping. Doping is a process in which we deliberately introduce some other atoms, and we change the intrinsic property of the semiconductor. We change this property. That process we call doping. And the substance which is added in the semiconductor crystal using the process of doping, we call dopant, or we sometimes also call the impurity that is added into the crystal and which change the property of the semiconductor. Now, extrinsic are of great importance for us, where their property, their conductivity is modified. Extrinsic semiconductor are of two types, N-type and P-type. N-type we call negative type and P-type we also call the positive type. So, N-type and P-type semiconductor. Let's first take about the N-type semiconductor. What is N-type semiconductor? N-type semiconductor are formed by doping the atoms from a pentavalent atom. Pentavalent from 15th group into the crystal. When we introduce the pentavalent atom in the semiconductor crystal, then these pentavalent atoms locate themselves at the site of the defect. When they locate at the site of the defect, they share the electron. They share the electron with the neighboring atom. And in this process of sharing the electron, because they have got the 5 electrons, so 4 electrons are shared and used in formation of the covalent bond. One excess electron, this is an excess electron, is available for the conduction. So with one atom of the impurity of the donor, we got one excess electron available. So electron density increases than that of the hole density. We'll say electron are now in majority while hole are in minority. This impurity is called the donor impurity because it has donated one electron. These impurities are added in very small amount, part per million, ppm. The adding of the impurity also modified the energy level. How it modified the energy level? This is conduction band. Suppose this conduction band has already few electrons, say 3 electrons, intrinsic charge carrier, and say 3 holes. And energy level of the conduction donor lies just below this is the lowest energy level of the conduction band. This is the uppermost energy level of the valence band, and energy level of the donor lies just below the conduction band, 0.01 electron volt below the conduction band. So result is that this energy level of the donor has got one extra electron. This electron can easily jump to the conduction band. So this way conduction band now has got the 4 electron while valence band is left only with the 3 electron. So electron increases then the hole. Number of the electron increases over the hole. And this type of the semiconductor we call N-type semiconductor. In the N-type semiconductor, although the number of the electron are more, but still it is neutral. There is no charge. Why there is no charge? Because every electron which is moving in the conduction band, which is moving in the crystal, in the lattice, it leaves behind a positively charged donor ion at the fixed place. So if the electron go out for conduction, then a positively charged ion is left behind. So overall charge is balanced. There is no negative charge in the N-type semiconductor, although electrons are more. Like we have done it in the N-type semiconductor, similarly in the P-type semiconductor, impurity or the dopant are from 13th group, that is trivalent. They are either aluminum, boron or indium. These atoms are there to be taken as an impurity or the dopant. They are doped in the pure crystal of the semiconductor, say silicon. When they diffuse into the crystal, they locate themselves at the site of defect. Say we are diffusing aluminum, which is trivalent, it diffuses and locates at the site of the defect, forming the covalent bond with the neighboring silicon atom. In this process, it shares 3 electrons, but it has got the deficiency of the 1 electron to share to form the 4 covalent bond. So at one of the bond there appear one excess hole. This is an axis hole, there appear an hole. This is the positively charged vacancy which can attract the electron. The electron may come over here and the hole may shift to this side. So with every impurity atom, there is one axis hole is available for conduction with a little bit amount of the energy, and the impurity now is called acceptor impurity. It is acceptor because it is readily available, the hole is readily available for accepting the electron, right? So what happened? With every atom there is a one extra hole is available, so hole density become greater than that of the electron density in this case. More hole are there, therefore it is called p-type semiconductor. In the energy level diagram, here we got the conduction band, there is already 2 electron, here we get the valence band, there is already 2 hole, but energy level of the acceptor lies just above the valence band. It's a very, very small energy. Now, since this energy level is unoccupied, it don't have any extra electron, it is unoccupied. So with the little amount of the energy, electron of the valence band of the pure crystal, silicon crystal, they can jump from valence band to this available energy level of acceptor. Result is that the number of the hole will increase. There was now 3 hole. Because this electron is not reaching to the conduction band, so conduction band the number of the electron remain same, say 2, while hole have increased. Either n-type of or the p-type, the electron density and hole density will change in such a way that their product will always remain constant and will be equal to the Ni square. Ni is a intrinsic charge density. So in the p-type or n-type, the product of the electron density and the hole density is always constant. Like n-type semiconductor, as we have discussed there, although in the p-type hole are more, but it doesn't mean that it is positively charged, because with every hole which is moving in the crystal between the lattice, in the lattice, there is an electron will come and fill up the place. So the ion, the acceptor ion will be negatively charged. So with every positively charged hole which is moving in the lattice structure, a negatively charged acceptor ion will be left behind. So simultaneously two things will be there, two charges will be there, hole which is moving in the lattice structure and the fixed acceptor ion, negatively charged acceptor ion. So therefore, like the n-type, p-type semiconductor is also neutral.